In this video, we're going to add a very crucial part of our analysis to encompass the idea of compounding interest. It's a bit of a slippery subject. It's one of those ideas that I think people tend to generally understand, but it's often hard to get a deep understanding of how compounding interest works. And so what I'm going to try to do in this video is really give you the logic behind compounding interest so that you understand how it works, and also understand why it exists, why we worry about different levels of compounding interest. In a lot of cases, it's really just about the practicalities of it, okay? So let's start out with an example here, kind of a silly example, but it's going to help us understand the logic. Let's say that I have $1 in student loan debt. I'm not going to add any money to my debt. I'm not going to take any away. It's just going to sit there in that account. And it's got a 100% interest rate that compounds annually, okay? So let's think about what would happen to our money over time, okay? Down here, I'm going to show you how much I owe. This Y just represents the year. So year 0, we're going to use this notation a lot in this class. Year 0 is now. That's like this moment, year 0. Year 0.5 is 6 months from now, half year from now. And year 1 is 1 year from now. So these numbers just represent how many years into the future we're talking about, okay? So at the beginning here, I owe $1. All right, that's our starting point in this equation. All right. How much am I going to owe half a year from now? If we have a 100% interest rate, I'm going to owe $1.50. All right, so it's going to grow half of its full amount in half a year's time. And then 1 year from now, I'm going to owe $2. All right. So here, between year 0 and year 1, we get that 100% growth rate that we would expect. Here's where things change, all right? With annual compounding interest, once we hit this point here, the math is actually going to change. We're going to continue to grow at a 100% interest rate, but the interest now is going to be treated differently because we're going to start the compounding process over. All right, so here's the deal. Here we're growing at 50 cents every half year, right, to get a full dollar. But once we get to $2, once we get to year 1, the compounding is going to start again. So now when we get to year 1.5, how much do you think we're going to owe? It's tempting to say $2.50. But if you do that, you haven't compounded at all. Now we need to start the interest over. We need to say, look, now you owe $2. Now you owe $2. And so after half a year, you need to owe another $1 on top of that. Right? We need to get 100% growth between now and the end of year 2, or the start of year 2, rather. Okay? So at year 1.5, you're going to owe $3. And in year 2, you're going to owe $4. See, here's the weird thing. With 100% interest, you don't have a constant growth rate of dollars. All right? And the periods where the compounding nature starts and restarts are really important parts of the mathematical process. Okay, so to try to explain that again, we're going to start over the compounding process in yearly increments. So in the first year, we grow at a constant rate. But once the year is over, we start growing at a new constant rate for the next year. All right, so here we're growing at 50 cents every half year. Here we're growing at $1 every half year. And then after that, it would change and continue to grow over time. So if you look at this sort of over time, what you would see is in these different increments, all the way through to year 3 and year 4, the growth rate is going to kind of look like this. It's going to move in these steps. All right, it's going to grow linearly over any yearly period, and then you're going to get changes in how fast it grows over time. All right, so what that means is within the year, the interest rate stays the same. The growth stays the same. But after the year is over, we start the process over. The interest compounds in annual increments. That's what annual compounding interest is. After the year is over, we start it over. Okay? It's kind of a weird process when you think about it, right? It's going to lead to these strange jumps. You know, the interest rate that you start paying in a year ends up feeling like a lot more than the interest rate you're paying right before the end of the year. So annual compounding interest, despite the fact that we use it a lot, is really kind of impractical. You would sort of hope that interest rates would allow for a more smooth growth over time instead of these big jumps over time, okay? And so, for that reason, we have different other alternative ways to think about how interest grows. So, what we might think about instead of an annual interest rate, let's think about one that compounds semi-annually, or compounds every 6 months, okay? Let's see if we can think about how this would look. All right, in both cases, you would owe $1 in year 0, all right? And in both cases, the first 6 months would be exactly the same, all right? If we're compounding annually or semi-annually, the first 6 months are the same because there's no additional compounding happening. So through the first 6 months, they grow exactly the same. But now, if you're managing this fund, see, after 6 months is hit, after half a year is hit, you say, well, now we got a new basis point. Now we got a new place to start over. So this rate now is going to be reapplied, all right? Now you're not paying interest on the dollar. You're going to start paying interest on the $1.50 because the compounding is going to start over, all right? So now we're going to grow to $2.25, right? This is a 50% growth rate, or half the 100%, right? But it's based on the $1.50, whereas this 50% rate is still based on the initial dollar, you see? So when you're compounding annually, what happens at the beginning of the year, that growth rate is going to be the same for the entire year. But when you're talking about semi-annually, it's going to kickstart. It's going to restart every 6 months, right? So you get from $1 to $1.50 and you start over and say, well, now it's going to grow based on you owing $1.50, all right? Year 1.5, again, it's going to kick in again. Every 6 months, it's going to grow based on the interest rate that you have here. So it's going to kick back in here. You'll now owe $3.38. And then it'll kick in again, and you'll now owe $5.06. Not worrying about any rounding there. And so what you can see here is, in both of these cases, the quoted interest rate is going to be $1. So if you go to a bank or something, and then you have an interest rate like this, they might tell you, 7% interest, and you might need to read the fine print to figure out how often it's compounding. And you can see that the result that we get can be pretty different depending on what compounding rate that they use. A lot of times students think that this is all about manipulation, that they're trying to just trick the customer, but what you should recognize is that any compounding level is really very arbitrary, right? There's no reason it should be annually necessarily. There's no reason it should be semi-annually necessarily. It's just how often do you want to think about when the compounding nature should be used. When it comes to things like savings accounts, they're usually compounded monthly. They're compounded monthly oftentimes just because that's when bank statements go out. So every month they start over, right? So the 30th of the month, they may say, this is the day we're going to compound. And all of our different rates that we have out there, all of our different savings accounts and everything, that's when we're going to compound, the 30th of the month. When it comes to the stock market, it essentially compounds all the time, right? If it's growing at a constant 8% rate, it's basically compounding all the time. When it comes to a lot of bonds, some are semi-annually, some are daily. Credit card debt, usually daily. There's all kinds of different rates, all right? So what that means is, since there's so many different ways to compound interest, we have to understand the difference. We have to understand how this works, okay? This is one of those things that you're going to see in this class over and over again. So let me go and give you the equation. It's going to look similar to something you've seen already. Here is our equation we're going to use for compounding interest. I'm just going to write it up here and then we'll explain. Okay? The future value is equal to the present value times 1 plus I over t raised to the nt. All right? Looks really similar to the formula we had in the last class. There's just one added term there, that t, that shows up in two places. That t represents the number of times funds are compounded in a year. T represents the number of times the funds are compounded in a year. Okay. So if you start getting into the financial world, you'll recognize that compounding really matters, and you're going to see a lot of different rates out there. I'm going to give you a couple of real-world examples for how compounding interest looks, and we want to make sure we understand why this matters. So at the end of this video, we're going to talk about practicalities and why this is done the way it is. So let's give you some math here. Before I even give you an example, I just want to point out one thing here, okay? What if it's compounded annually? Okay? What would T equal? If T is the number of times the funds are compounded in a year, then what would T equal if we have annual compounding interest? Well, T would equal 1, okay? So if T equals 1, then the future value equals the present value times 1 plus just I, right? If T is 1, I divided by 1 would just be I raised to the N, right? So that formula we used in the last video, here it is. It's annual compounding interest. If you're using annual compounding interest, this is our formula, all right? A lot of times we use this just for simple calculations. It's kind of like our baseline way of thinking about things a lot of times. But if we want to get specific and actually think about values, a lot of times we have to use what's really happening in the real world, which is not typically annually compounding interest. Instead, it's something else. So let me now give you an example. Say that I have $8,000 in a savings account. Pays a 4.65% interest rate. Compounded monthly, which, as I mentioned before, is most common. It's not always the case, but it's most common for savings accounts to compound monthly. And that, again, has to do with just the practicality of the fact that banks usually deal monthly. They usually deal with sending out statements and everything every month. So that's when they apply their compounding changes. So let's say, how much would I have after 20 years? I don't do anything to these funds. I just let them grow. Okay. And let's face it, this is an easy question, right? It's easy because all we're doing is just plugging into the formula here. So there's not really anything too challenging about this. But, you know, I'm not trying, my job in this class is not just to teach you hard stuff, it's to teach you useful stuff, all right? And to me, this is very useful. So I'm just going to plug in the values, put them where they go. Future value equals the present value, which is known to be $8,000, times 1 plus 0.0465, right? That's that interest rate right there, written in decimal form. Divide that by, what do you think goes here? T is the number of times it's compounded in a year. So if we're talking about monthly compounding interest, this would be 12. Okay. And I'm going to multiply that times n times 12. 20 years at 12 increments. Notice this right here is the number of times it'll be compounded totally, right? If we multiply these together, you know, you got 20 years, 12 periods of compounding changes. This is the number of compounding times that it occurs, okay? So there we go. Let's see what I get. You guys should be doing this on your calculator too. I know it's tempting just to watch me do this, but I'm telling you, people make mistakes when they don't practice. So let's practice this. And it looks like what you should get here for the future value is 20,239.67. Okay? So that's what you'd have after 20 years. Let's compare that. What if instead you go to the bank and let's say a bank down the street is offering the exact same interest rate and you don't read the fine print, but the bank down the street is doing annually compounding interest. Okay? So in this first example here, we did monthly. How would this look if it was annually? First of all, would that be good or bad for you if it was compounded annually? Would that be good or bad? Relatively speaking, that would be bad. When you're saving money, more compounding periods are good. When you're borrowing money, more compounding periods are bad, right? The more times a fund is compounded, the faster it grows, all right? So more growth is good when you're the saver. More growth is bad when you're the borrower. So the future value here will look like this. All right, t goes to 1, so I don't need to worry about t. It effectively goes away in the formula. And so this would be our equation here. And so the answer that I get looks like this. You'll notice that it is not, outrageously different. There's not a huge difference between these values. But, $400 or so, it's significant, right? It's still a lot of money. And so you wouldn't want to make these types of mistakes. So if you're shopping around trying to find a good interest rate as a saver or a borrower, you're definitely going to want to pay attention to the number of times that are compounded. Okay. All right, so now let's think about an example with debt. All right, still dealing with a compounding interest problem, but let's think about it now in terms of debt. So let's take a quick look at this question here. I have $400 in credit card debt. The interest rate is 19.9%, compounded 360 times per year. How much will I owe after 6 months? I intentionally made this question a little bit trickier, but let's face it, in the real world, we don't always use with really even numbers or anything. This is a very reasonable question. This person has $400 in credit card debt. I want to know how much debt I'm going to have half a year from now. So maybe something a college student would face. By the way, this interest rate on the credit card debt, really common. 19.9% is a rate I see pretty often on credit cards right now. And this 360 times compounded in a year is really common. I think the logic is a lot of months have 30 days. So if you do 12 times 30, you get 360. I can just tell you that it's very common. I don't know exactly why it is, but it is. All right. So you'll see 360 times a year a lot of times with credit cards. Sometimes you'll see 365 times a year. These are all very common rates. Okay. So I want to figure out how much debt I'm going to have. Well, let's apply the formula here, and we got to be very careful. All right, so here's where we got to be careful. We've got our interest rate. Plug that in, no problem. But what do we put for t? All right, you got to be real careful here because I think it's a little bit tempting to put 180. All right, the logic here is you've only got half a year, so it's only going to compound 180 times. But that is not what t tells you. T is not how many times you compound in the question. It's how many times does it compound in a year. All right, so I'm still just going to put 360 because that's the number of times it's compounded in a year. The fact that it is only half a year is going to be used to figure out what's going on here with n, but it's not going to determine what happens with t, okay? So I'm still going to use 360 there. What am I going to put for n? What do you think I'm going to put for n? N is the number of years. So n is actually going to be 0.5, half a year, all right? Mathematically, it works out just fine to use half a year. And again, that's completely reasonable to wonder how much debt you would have half a year from now. So there would be our equation. All right. A little bit messy, but the logic is sound. So I'm going to solve for this, see what I get. And so what this comes out to is $441.84. All right, that's the answer that I get. And of course, if we compounded this just annually, you would get a smaller number. If we compounded it 365 times, like a lot of credit cards do, you get a little bit higher of a number there. The thing about interest, and I hope you understand this, the more periods you got, the more years we're talking about, the more interest becomes important, right? So this credit card debt, if we take this thing out to 50 years, you're going to get, this huge number. So the more periods you have, the more times you have in terms of years and in terms of compounding periods, the larger it's going to grow and faster it'll grow over time. Okay, so that's the logic of compounding interest. We can use it to solve for future value. We can use it to solve for present value, right? That's just rearranging the formula. Nothing new, except the formula is just a bit different. We could even use it to solve for the interest rate or N. I don't think I'm going to worry about doing that in this class. Frankly, it's sort of an unnecessary exercise to solve for the interest rate or N, because annual compounding interest does a pretty good job of approximations anyway for us. Okay, so in terms of compounding interest, I think you've got everything you need to go through and solve for all those practice problems that I gave you, and you definitely want to make sure you practice.